Okay, now we're going to look at a specific kind of integration that involves expressions of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared. Now I use the x here, but pay real close attention to where the variable falls in these expressions. So we distinguish between a squared minus x squared, where the variable is after the minus sign, and x squared minus a squared, where the variable's positive. So it makes a big difference on which of those two forms it is. Okay, now what we're going to be doing in each of these cases is, depending on the form, we're going to use a specific trig substitution. If your expression is of the form a number squared minus x squared, the variable squared, you're going to use the substitution x equal to a number, whatever the a is in this original expression, times sine of theta. Now the reason we're doing that is that we're going to be taking advantage of the Pythagorean identity that says that 1 minus sine squared of theta is equal to cosine squared of theta. So by making this substitution, we're going to end up getting 1 minus sine squared in that expression, and then we're going to be able to change it from this difference to just a single term. And that's real important, because a lot of times these end up underneath the radical. And if you can change a difference or a sum into something that's just a product or a single term, you then can remove it out of the radical. So that's the point here of this particular type of substitution. Okay, now the second one here is the a squared plus the x squared. When you have this form where it's the sum of the two squares, you're going to always use the trig substitution, x equal to the a. Again, the a is tied to what that original term was, a times tangent of theta. Okay, now the reason is you're using the trig identity, 1 plus tangent squared. You're going to end up getting that expression if you use this substitution, and then you're going to change it to secant squared of theta, just using the Pythagorean identity. And then the last one here is going to be where you have the variable that's first minus the number squared, and in this case you're going to use the substitution x equal to a secant of theta. And then what you're going to end up with is you're going to end up with an expression here. See, when you put this secant theta in, you're going to end up getting a squared secant squared theta minus the a squared, which once you factor out the a squared, you're going to end up getting this secant squared theta minus 1. Now remember our trig identity up here. Secant squared minus 1, if we just move the 1 to the other side, this is equivalent to tangent squared of the angle. So now again, we have taken something that had a difference here, which if that were under a radical, we couldn't do anything to simplify it. But now that it's just a product of things, we could actually remove it out of a radical. So each time it depends on where the variable falls and what the signs are between the terms. So learn these three particular substitutions and know when to use them. Which form requires which one. Okay? And also now we're going to end up having to go back to our right triangles, because at the end, when you make this substitution, let's say I said that x is equal to a sine of theta. At the end, I'm going to end up with an integral that has a bunch of thetas in it, no x's. So what I'm going to have to do is I'm going to have to go back to my x's. And the way you'll do that is you'll take the substitution, whatever substitution you used, and solve it for the trig function. So that means that sine of theta is x over a. So if this is theta, that means that x is the side opposite and a is the hypotenuse. Use your Pythagorean theorem to get the other side. Now the hypotenuse is a. This side is a squared minus x squared. Take the biggest side minus the other one squared. Okay, and now from that, if I'd had a tangent of theta in my answer, I know tangent will be the opposite over the adjacent, so the x over the square root of a squared minus x squared. So we will need to use these at the end to go back to our original variable. So each case, had I used the substitution x equal to a tangent, that's equivalent to tangent of theta equal x over a. So if this is theta, opposite over adjacent, so this is x and this is a, and that makes this other side has to be the sum of the squares of the other two. And now you can use that to go back to your original variable x. And then finally, the last one, if we had the substitution x equal to a secant, then secant of theta would be the x over a. Well, secant, if this is theta, secant is the hypotenuse over the adjacent. So this would be the x, this would be the a. It's the square root of the hypotenuse squared minus the other side squared. And now you can use that right triangle to go back to your original variable x, because you'll end up with a solution to the integration that has thetas with the trig functions.